Basics of probability. So we're going to look at relative frequency, simulation, joint probability, and its interpretation. And this is all a primer for information. So big data is not necessarily random, but it can be. Noise can occur in any data set, big or not. Chaotic variables and random variables have distributions. So we can get distributions which are bar graphs or histograms, and classifiers are predictions between 0 and 1 inclusive, and often closeness to an extreme is a measure of confidence, and so we often treat them as relative frequencies. So probability theory is important even if we're not looking at something that's random. But let's start at the beginning. So the sample space S of a random process is the set of all possible outcomes. It's in the universe of possibilities. An event is a subset of the sample space. The probability of A, denoted probability PR parentheses A, is the likelihood that A occurs. And events in the universe that are outside of the set of all possible outcomes have a probability 0 of occurring. So the sample space of a random process is also the set of all possible outcomes of that process. For now, we're only going to look at finite sample spaces. For example, a single coin toss can have a sample space of heads, tails. A roll of a 6-sided die has a sample space of 1, 2, 3, 4, 5, 6. An event is a subset, A, of the sample space S. For example, A equals heads is the event of getting a heads while flipping a coin. A equals 2, 4, 6 is the event of rolling an even number with a die. The probability of an event A occurring is denoted the probability of A, and to get that, we look at the count, C sub n of A, the number of occurrences of event A in n trials. And then the probability of A is the limit as n goes to infinity of the count of the number of times that A occurs in n trials divided by n. Now, probability can be defined and interpreted in many different ways. So, limit of relative frequencies, which is the one we saw on the previous slide, likelihood of an event occurring, a concept related to information, but interpretations don't change basic results. So in one toss of a fair coin, the probability of heads is a half. In one roll of a fair die, the probability of 1 is 6. The probability of an even number is a half. Now, we can associate a variable with a process or a sample space. So if we have a sample space S of all possible outcomes, then a variable X is associated with the process, a sample space S, if X can attain any value in S, and any trial of the process, the value of X is in S. So for instance, what would we get if S was clock outcomes? So this isn't a random process, but X would have to be a valid clock time to be associated with the set of possible outcomes of a clock, S. A variable associated with a random process is a random variable. So if we have, for instance, X associated with the set S of heads or tails, then X has to either be heads or tails. X associated with the set 1, 0, X is either 1 or X is 0. A random variable is just a variable. The word random says how a random variable gets its values, but a variable is an unknown, something that can take on different values, just like you saw in high school algebra. A trial is an instance in which a random variable takes on a value. So if X is associated with a set S of heads or tails, then trial 1 may be as X is heads, trial 2 X is heads, trial 3 X is tails. So each time X takes on a value, then that's a trial. And randomness means we never know beforehand exactly which value X will take in any given trial. An observation is data about the values of X collected over many trials. Now, probability in random variables, we often index the outcomes. So S would be O sub 1 up to O sub j up to O sub capital M. The probability of a random variable x being assigned an outcome O sub j can be written as probability parentheses x equals O sub j, or probability parentheses x equals j, or just p sub j. So these are all notations we use for the same thing. The toss of a fair coin, S be tails or heads, we'll call that outcome O sub 0 and O sub 1 respectively. The probability that x is a heads would be the same as the probability that x equals the outcome O sub 1. Or a lot of times we'll just say the probability that x equals 1, the index of the outcome, or p sub 1, and in all cases, if it's a fair coin, that's a half. Now, if we have x associated with a set S of outcomes, then the probabilities are non-negative for all O sub j, j equals 1 up to m. The sum of the probabilities is equal to 1, so one of the outcomes has to occur. Now, in subscript notation, we would write p sub 1 plus up to p sub j plus up to p sub m equals 1. Now, we use capital X for the variable, and a lot of times we do that so we can use the lowercase x as the index instead of j. So capital X would be associated with S, which is O sub 1 up to O sub lowercase x up to O sub m. The probability that x equals little o sub x could then just be written in function form as p of x. And so you notice the clever use of notation here. It says we're using the variable x and asking what the probability of it taking a index lowercase x outcome is. So p of 1 plus up to p of x plus up to p of m equals 1. So probability notation, there's a lot of notation in probability. We label the outcomes of a sample space. Remember, we're only going to look at finite for now. A random variable associated with S is just a variable x. It takes values in S. The probability that x equals O sub j is the probability O sub j occurs. We write p of j or p parentheses j in place of probability capital X equals O sub j. And to really indicate it, a lot of times we'll use lowercase x in place of the j. So the frequentist idea of the probability of an event is we conduct n independent trials of the experiment, which we often refer to a random process of some kind as an experiment. If A is an event, then we look at the count, C sub n of A, the number of occurrences of A in n trials. The probability is then the limit as n goes to infinity of the count of the number of times A occurs in n trials over n. We call this thing a relative frequency, the C sub n of A over n. And the limit as n goes to infinity means we want to think of probabilities when n is very, very large, many, many, many trials. For example, if A is heads, the event of heads, and we have a fair coin, then the count of A is about 1/2 n, so about half the time we'll get heads as n goes to infinity, because the probability of fair coin returning heads is a half. So we can look at this pictorially. So we have here a little simulation. Notice that the probability is a half in this simulation. The relative frequencies aren't anywhere close to a half. That's what we see there. So for small values of n, so for lower number of trials, we're not close to the 1/2. But notice that as n increases in size, the relative frequency approaches the theoretical probability. So there's actually a theorem which says that this happens, called the law of large numbers. And so you can see that for very large numbers of trials, the relative frequencies become very close to the actual probability. We'll look at it again when probability of heads is 0.25. Notice again, we don't start out close to 0.25. So for a small number of trials, the relative frequencies are not that close to the actual probability. But as the number of trials becomes arbitrarily large, the relative frequencies approach the theoretical probability. So joint probability. We have a sample space S, and now it's going to be doubly indexed because we're going to have two variables. So S is O11 and O12 and all the way up to O sub xy, where little x goes from 1 to m sub x and little y goes from 1 to m sub y. And the variables xy associated with S implies that an outcome O sub lowercase xy corresponds to the variable capital X taking on the index value little x, and the capital variable y taking on the index value lowercase y. P of xy, the probability that x equals the index x and y equals index y. And what we really mean here is that the outcome O sub xy occurs. That's the probability in a given trial that we get these two indices, and therefore that outcome O sub xy. So P sub xy is a joint probability distribution, and simultaneous is going to mean in the same trial. So let's elaborate on that. So P of xy is the probability that x equals x and y equals y. That's the joint distribution of x and y. And it's the probability that capital X is equal to little x and capital Y is equal to little y at the same time. And what does at the same time mean? Simultaneous, we mean in the same trial. Marginal probabilities, if you've got a joint probability distribution, P of xy, then we would like to be able to recover the probabilities for the individual variables x and y. And those are the marginals. So the marginal probability of x is the sum over the y's of the joint probability distribution, P of xy. And likewise, the marginal distribution of y is the sum over the x's of the joint distribution. And if there's no confusion, then we'll simply write P of x and P of y as the probability distribution of x and y respectively. And these are the marginals, of course. Now, variables x and y are statistically independent if and only if we can write the joint probability distribution as the product of the individual marginal distributions. Now, we'll just take this as a definition for the present. It's actually a consequence of a thing called information theory. Independence means an outcome for x occurs irrespective of the value of y and vice versa. So in other words, x doesn't care about y, may not even know it exists, and vice versa. So variables x1 up to xn are identically distributed if each has the same distribution P of x. And in that case, the joint distribution of all of them would simply be P of x times itself for indifferent index variables. Variables x1 up to xn are independently and identically distributed if they're identically distributed and also independent. The law of large numbers, as the number n of independent trials of a process increases, averages of the independently identically distributed outcome variables x sub I approach an expected value in the limit as n goes to infinity. And notice the key word here, independent trials. And relative frequencies are often very close to a limiting value. After only a few thousand trials, we've actually already seen that. Many independent trials implies many independent variables. Many patterns emerge. For example, you could have 20 consecutive tosses of tails, 18 heads in a row, and then a tails. Now, this almost certainly would not occur in 100 tosses of a fair coin, but almost certainly does occur in 1,000,000 coin tosses. So we have to be careful when we look for patterns in random processes. They're not really there. we couldn't use this run to predict if a coin is fair, for example, because this is a pattern that comes about just because of randomness. Now, the larger your data set is, the more patterns like this that can occur, and nowadays we often work with data sets that are billions or trillions or even larger of data points. Now let's look at an example. Let's look at small variations about a mean. So the data here is speedometer readings since 3 p.m. for N automobiles on a certain stretch of highway. So there's the speedometer readings. Each is attempting to drive 40 miles per hour at all times. But there are small random variables that affect that speed. No one's perfect. There'll be some slopes and some curves, and so the needle will move a little bit, even though it's trying to keep it at 40. We're also going to assume that each driver is independent of every other. So these are well spaced. There's a lot of room between the individual automobiles. Automobiles sufficiently far apart with an overall average speed, maybe there are a few outliers, a few leadfoots. That implies a model of the form, the data is the average speed plus the noise, where the noise is the variations. Mathematically, if S sub j is the speedometer read out of the jth car at time t, then S sub j is equal to mu, which is the average speed, plus R sub j, which is noise at time t. The average value of the R sub j has to be 0 because mu represents the average speed of the automobiles altogether. So the automobiles are not communicating with each other, then these noise terms are independent, and so the S sub j would be independently and identically distributed. So we're going to look at well-spaced cars. They don't care about the other cars in the highway. They're independently trying to stay at 40 miles an hour. And the variations are not unique. Any car could have the same issues with slopes and stuff like that. So these R sub j are identically distributed. The S sub j are independently of each other. These are IID variables. So what we have is a set of data. This is actually simulated data. And you can see what happens for automobile 1, S1, a lot of little variations around 40 miles per hour. Same thing with 2 and all the way down through the nth automobile. And even though these are independent processes, they're all trying to drive the same speed. So they average to that common speed. As a matter of fact, if you start looking at averages, the law of large numbers says the averages should approach that mean. And sure enough, the average of all of them divided by the number of automobiles is 40 miles per hour. So in summary, a variable is random if it's associated with a process that assigns it a value at random. The probability of a given set of values is how likely the variable is to have a value in that set. In many situations, we have a lot of random variables, and very often they're independently identically distributed. We may have one trial independent of thousands of other trials, or a corn plant's height being a random variable in a large cornfield. And much of the mathematics, as you've seen, is about notation. So you'll need to know what these symbols mean, but that's a lot of the battle.